This brings us to the final workshop of the course. In this workshop, we will study the effect of bolt preload on the overall stiffness of a structure. To address this, let's study a type of connection used in turbines known as a bolted disc drum connection. In turbines, we commonly find a series of rotors with different radii mounted on a common shaft. These rotors consist of discs on which the blades are mounted. The rotors are sometimes flanged together using bolted joints. In such cases, the preload in the bolts is an important assembly parameter as it can change the vibrational characteristics of such a system. It's very important to study the dynamic characteristics such as natural frequencies for such systems, as this equipment rotates at very high speeds and can fail catastrophically under any instabilities. So the objective of this workshop is to create the model for one such system and calculate its natural frequencies under different bolt preloads. Here's the disc drum system that we will work with. It has 3 discs of different diameters that are connected by 2 drums. The connection is established by 3 sets of 8 bolts each, which carry the bolt preload. Frictional contacts with a coefficient of friction 0.2 are used to model the contacts between the discs and drums. We will run a series of simulations to study how natural frequencies change with bolt preload. The stresses in the bolts are not of interest, and sliding between the bolt head and the parts is not significant. So we will model the bolts using beam connections. In each design iteration, we will perform a static analysis to calculate the pre-stress in the structure due to preload. For the boundary conditions, we will fix the 2 ends of the discs, as this is where they are connected to the shaft. It is important to study the dynamic characteristics of the structure under rotation. So, we will apply a rotational velocity of 500 rpm to the entire structure. We will use 3 load steps in each simulation. The first load step is used to apply the bolt preload. We lock it in the second load step and start ramping the rotational velocity. And in the third load step, we will maintain this speed. This analysis is followed by a modal analysis using linear perturbation to calculate the modal frequencies and the corresponding mode shapes. Once we have all the results, we will see how the modal frequencies change for each case, and we will investigate how the bolt preload is affecting this. So let's get started. Start a new workbench session and insert a static structural module. Download the provided geometry file, disc drum connection, and attach it to this module. In this exercise, we will use the structural steel material for all the parts, so we need not create any new materials in engineering data. So go ahead and open mechanical. We will use metric units for this exercise, so go ahead and set the units accordingly. Before we begin, let's insert a cross-section view to see what the assembly looks like from inside. One way of doing this is to expand coordinate systems, right-click on Global Coordinate System and insert a cross-section plane. This will section the geometry at the XY plane of the coordinate system. By doing this, we will also be able to access different edges and surfaces that are hidden inside. This will come in handy while creating beam connections and other objects. We will use named selections for defining the beam connections for bolts, So the first order of business is to create the named selections. We will use a naming convention to identify the pairs properly. So let's call this as joint 1, this joint 2 and this joint 3. We can now identify the two pairs of each joint using this name. Select the edge of one of the holes, right click to create named selections. Name this as joint 1_1. We want to pick all the holes on this plane that are of the same size, so go ahead and toggle the boxes for size and location X. Repeat these steps to create the named selections for the holes on the other side. Select the inner edge, right click and select Create Named Selections. Once again, check the options for size and location X and name this named selection as joint 1_2. Now go ahead and repeat these steps to create the named selections for the other two joints. In case of joint _2, note that the disc is sandwiched between the two drums and we use beam connections to connect the two discs. So remember to pick the edges from the inner face from both the drums for creating named selections. Okay, so now we have created the named selections. Next step is to create the beam connections using Object Generator. Let's start with joint 1. Go ahead and create one beam connection which can be used as a template to create others. Now select this beam connection and go to Object Generator tab under the Automation tab. Select the reference to be joint 1_1 and mobile to be joint 1_2. We need to specify a range of distance between the surfaces. To find this range, select both the surfaces and go to Home tab and click on Selection Information. This tool will provide the distance between the two surfaces. Now use this to define the minimum and maximum limits of the distance in the Object Generator. Hit Generate and this will create the beam connections in joint _1. Once they are done, select them all, right click and group them under the name Set 1. This way, we can easily identify them when we have the other two sets created. Now follow the same steps to create beam connections for the other two joints as well. We now have all the beam connections created, but before we collapse the connections tab, let's define the contacts between the drums and discs. We notice that the contacts are already created during geometry import. Let's verify them to see if there are any unwanted contacts. They all look good except that they are bonded and not frictional as we wanted them to be. So let's change that. Select all the contacts, change the contact type to frictional and define a coefficient of friction of 0.2. To refresh your memory, we discussed in lectures that using small sliding option for contacts where we don't expect gross sliding can save us some computational time. Since we are planning on running multiple design iterations, let's make use of this option. Under the same contact objects, locate the option for small sliding and change it from program controlled to on. With this change made, we can now move on to meshing the assembly. Before we mesh, let me remind you that the contacts contribute to the overall stiffness of the structure, and using a fine enough mesh at contact regions is important to capture the stiffness accurately. So we will use mesh controls to refine the mesh at contact regions. To do this, select the contacts and drag and drop them onto the mesh object in the model tree. This will create mesh sizing objects at the contact regions. Use a mesh size of 10 mm to have a fine enough mesh in these regions. Now right-click on mesh and hit generate to generate the mesh. We can see that the mesh near the contacts is finer than the rest of the assembly. This way, we can obtain results with reasonable accuracy without having to increase the solve time. Next, let's define the analysis settings. Set the number of load steps to 3 and turn on the large deformation. Now let's move on to defining loads and boundary conditions. Select the two faces on the outer discs and define a fixed support on them. This is where the disc drum assembly is mounted on the shaft. Next, let's create bolt pretension objects for each of the beam connections. To do this, go back to the connections object, expand set 1, select all the beam connections under it, drag them and drop them under static structural to create bolt pretension objects for each beam connection. Now we need to define preload for each of them in load step 1 and log them for rest of the steps. To edit them all at once, select them. Next, select the load step from the graph window and now edit the pretension object. Define a preload of 100 Newton. Next, select load step 2 from the graph window and go back to pretension object and set it to lock. Now select the load step 3 and check if the pretension is still set to lock. Everything looks good. So select all these objects and group them under one folder and name it set 1. Now repeat these steps to define bolt pretension for the other two sets of bolts. One last load that needs to be defined is the rotational speed. Remember that the turbine rotates at high speeds and this can generate some stress in the parts due to inertial forces. So let's add a rotational velocity condition, change the definition to components and define an X component of 500 rpm. This condition is ramped from 0 to 500 in load step 2. So change the table accordingly. Now let's proceed to defining results that we are interested in. Insert total deformation, equivalent stress and contact tool. That concludes the setup of static analysis for case 1 with a bolt preload of 100 Newton. Now let's set up another case for a preload of 500 Newton. We don't have to repeat all the steps. Instead, we will duplicate the system and only modify the bolt pretension objects. Right-click on static structural and click on duplicate. This will create a new static structural system with all the previous definitions. Now one by one, expand the groups of bolt pretension objects and change the pretension load to 500 Newton. Remember to edit them all at once for efficient pre-processing. Once that is done, Rename the first static analysis to case 1 preload of 100 Newton and the second static analysis to case 2 preload of 500 Newton so we can identify them easily. Now it's time to define modal analysis for each of these static analyses. To do this, go to Analysis under Home tab and select Modal. This will create a new modal system in the model tree. Now let's bring up the workbench window once and look at the three systems that we have. We can see that they all share the data with engineering data, geometry and model cells of system A. Now go back to mechanical window, go to the modal system that we had just created and under pre-stress select the first static system which is for a preload of 100 Newton. Now go back to the workbench window again and see the system now. We can see that there is a new connection between the solution cell of static and the setup cell of modal system. This implies that the results from the static analysis, which includes the updated stiffness matrix, are used in setting up the modal analysis. That's linear perturbation for you. Now let's get back to mechanical and create one more modal system and set its pre-stress to the other static structural analysis, which is for the preload of 500 Newton. We now have the static and the modal analyses set up for two cases of different preloads. Let's go ahead and solve all the systems. One way of submitting all four of the jobs at once is to select the four systems and hit solve. This will submit them in a sequential way. We can also solve just the two modal systems and they will automatically solve both the static systems too. This is because the modal analysis uses results from the static analysis, so we cannot solve it without having the results from the static system first. This may take a few minutes to solve depending on your system. Alright, so now we have the results. Let's study them, starting with the modal frequencies from both the cases. We can access them from under Solution of Modal System. We have extracted 6 modes each from both the systems, which is the default setting. From the mode frequencies for the first case, we notice that the modes 1 and 2 and 5 and 6 are very close to each other. Let's plot the mode shapes for each mode and study them to understand them better. To do this, select all the modes, right-click and select Create Mode Shape Results. This will place relevant result objects in the model tree. Go ahead and evaluate them. Let's use multiple viewports to review these results at once. When we play the animations for each of these modes, we can see that the modes 1 and 2 are bending modes in two orthogonal directions, which explains why their values are so close to each other. This small difference can be further reduced by using a finer and uniform mesh. Mode 3 is a torsional mode and mode 4 is an axial mode. Modes 5 and 6 are again two similar modes in orthogonal directions and therefore their values are close to. Now let's look at the modes from case 2 where the preload is 500 Newton. First of all, we can notice that the frequencies of all 6 modes are higher than those from case 1. Let's go ahead and plot their mode shapes. We can see that again modes 1 and 2 are bending modes in orthogonal directions. Followed by mode 3, a torsional mode. Mode 4, the axial mode. and again modes 5 and 6 are in orthogonal directions. So we see that the system has the same first 6 modes, but their mode frequencies are higher in the case with higher bolt preload. To explain this, let's look at the results from the static analysis for both the cases, starting with equivalent stresses. We can see that the maximum equivalent stress increases in case 2 compared to case 1. This explains that due to the higher stresses in case 2, the structure is stiffer and therefore is expected to have higher mode frequencies. But stress is only one aspect of it. Remember that this is a non-linear analysis due to large deformation and frictional contacts. So the overall stiffness is expected to change. Let's investigate the contact using the contact tool. Under the contact tool, we will use the status option to see what portions of the model have contacts closed that are sliding and sticking. We can see that the portions of the contact that are closer to bolts are closed and are in a sticking state. This indicates that regions closer to bolts have higher contact stiffness. This is due to the pressure cone created by the bolt preload. Since higher bolt preload results in larger pressure cone, therefore we can expect more contact area and therefore higher contact stiffness as well. We can verify this by plotting the contact areas and stiffnesses for individual contacts using contact trackers under solution information. So all these results show us that the bolt preload introduces stress stiffening in the model, and at the same time it also increases the contact area, which additionally increases the structure's stiffness. So in terms of the governing equations, it is affecting both the K and the S matrices. This explains why increase in the bolt preload can increase the overall stiffness and therefore the mode frequencies as well. With this, we can conclude this workshop.